In the last video, we saw that a current carrying wire experiences a force when interacting with the magnetic field. So I want to look at a specific situation of that. So what I've done is I've taken a loop of wire and I've encased this wire in a magnetic field. For purposes of clarification, I suppose I should say that this is a square. I've tried to draw it in 3 dimensions. The field doesn't look particularly uniform here, but 3-dimensional square completely encased in a uniform magnetic field, where this is carrying some current I, and each side of the square is A. So A. The current is uniform, the magnetic field is uniform. And let's just ask ourselves, what does the force look like on this loop? The first thing I would say is that if I'm going to actually determine the magnitude of the force, probably the easy way to do that would be to break this up into sections. Look at the force on this section, this section, this section, this section, and then add it all together. Forces are vectors after all. I should be able to add them together. So the first thing to do, I would think, would be to determine the magnitude of the force on each different side, and then look at the directions of those forces and see what we can come up with. So let me remind you of this equation. A long straight wire in a uniform magnetic field carrying a uniform current experiences a magnetic force of this form, I, L, B sine of theta, where theta is the angle between the current direction and the magnetic field. I've tried to draw this such that the magnetic field is perpendicular to the face of this loop. In other words, this is a loop of wire, but if I were to fill in the gap, the magnetic field would be perpendicular to it. A little hard to draw that on a 2-dimensional surface, but that's the idea. So everywhere, in every leg, the current and the magnetic field are perpendicular. So the sine theta, for this case, just goes to 1 everywhere. And so the force on each of these sides is the magnitude of the current times the magnetic field times the length of the wire. And so if I'm doing it on each individual side, the length of the wire in each case is just A. And so let me number these. We'll say this is side 1, side 2, side 3, and side 4. I can now write this, the magnetic force on side 1 by magnitude is just going to be IAB. Of course, if this is truly a square and every side is side A, then this gets really easy because now the magnetic force on side 2 is just IAB. And make sure I don't run out of room here. The magnetic force on side 3 is also IAB. And I think I have room. Yeah, magnetic force on side 4 is also just IAB. And so because of how I've constructed this wire, the magnetic force on all sides turns out to be the same. Again, please keep in mind, we are assuming a uniform constant magnetic field and a uniform constant current, at least constant in magnitude. Of course, the current changes direction, but within each leg, the current is uniform, just changes direction at the corners. So now I've got the magnitudes. It becomes a matter of looking at the directions. And so for that, I'm going to use my right-hand rules. Let's do leg 1. It's going to be a little hard to, it's really hard to see in this orientation. Let me redraw it small over here. So there's my current. This is just to help me see through the geometry. There's my current, and if I'm facing this loop, then it looks like my magnetic field is everywhere into the page. You see what I've done? I've just flipped around my drawing, and so I'm looking at it face on. This is going to make it easier for me to see the directions of the force. So if I'm looking at at side 1, which will be this one, put my fingers in the direction of the current, curl them into the direction of the field, and stick out my thumb. And I get a force acting on side 1 that is upwards, like that. Okay? Let's do side 3 next. just to show you how this works, fingers in the direction of the current, curl them in the direction of the field, move my hand up, stick out my thumb. I'm gonna get a force pointing down. So side 3 experiences a force pointing down. I did that to show you that you can just, if you've done one of these, you can do the rest of them, or you can do the opposite one, I should say. If a current to the right produces a force up in this magnetic field, then certainly a current to the left will produce a force down in the same magnetic field. Let's do side 2 over here, then we can use that to do side 4. So side 2, which is right here, fingers in the direction of the current, curl them into the direction of the field, stick out my thumb, I get a force on side 2, acting, I should draw like that, acting, let's do this, try to show the three-dimensionality, acting to the left, it would be pointing this way. That means, of course, over here, because my current is opposite direction to this one, I'll get a force over here that looks like that. All right, I think that works okay. So what's going on here? Well, every one of these forces is the same magnitude. They're all IAB because the field and the current are both uniform. Well, if that's the case, then certainly the total force on the loop has to just be 0. This force is going to cancel with this force, and this force is going to cancel with this force. That's really interesting, and it turns out that that's true. The net force on a closed loop is equal to 0. This is for a closed loop in a uniform field. I can't say that enough, because if the field is not uniform, or if the loop is not, it's in some sense it's always going to be closed if the current is running through it. But if the loop has, let's just go with this. If it's a closed loop in a uniform field, that's really what I want to stress, the uniform field. If those are the case, then you've got a total magnetic force acting on this loop of 0. And we did this for a square, but as it turns out, this is a general result. If I were to make this a circle, or a triangle, or a rectangle, or some crazy shape, then the total force acting on that loop would still be 0. That is a general result. That actually leads to a way to make some problems simple. Let me give you an example. This is just a simple example. Let's say that I have a current loop that looks like this, where this is some side L, and this is some sort of circular arc. And I place this loop into a current, place this loop into a magnetic field. Let's put it into the page, why not? A uniform magnetic field. I forgot to label my current. I labeled this as some side L, but I forgot to label that this is a current I. And that makes this magnetic field B. And let's say that, suppose you were asked to determine the magnetic force on the top side of this loop. So you have the bottom leg here, the top side. And suppose that the question asked you, well, what is the what is the magnetic force acting on the upper portion of this loop? That's actually not super easy to do, especially we don't know any formulas to do that. To actually work that problem, you'd have to do a little bit of calculus. Not terrible, but there's an easier way, right? If you know that the total force in this loop is 0, then certainly this statement has to be true. The force on the bottom has to equal the force on the top. That has to be the case. If they're going to add up to 0, whatever's acting here has to be the negative of whatever is acting here, and vice versa. They have to be equal in magnitude and opposite in direction, and we can take care of both of that by saying this: the force on the bottom has to equal the force on the top. And the hypothetical question asked you about the force on top, but if you know that the force on the bottom is just ILB, then the force on the top has to be ILB. Not a big deal. This works if this is any crazy shape. It actually works even in some situations where you might go, well, I can't do that there. So let me give you another problem, another hypothetical problem. where I just have a section of a larger current, and say the current is here, and this is some sort of circular arc where this distance is L, but there's not actually a current here. So, and let's say the question is, well, what's the force, magnetic force on this? I'm going to put it in the same magnetic field as here. I won't draw it in the interest of time. But what's the magnetic force on this thing? Well, you go, well, okay, I can't really use this here. Or can you? If you imagine that there's a connecting branch carrying the same current, you know that the force on that branch is just ILB, which means that the force on top here would have to be ILB. What have you changed by just imagining that that's there? You changed nothing about the actual force acting here. You didn't change the magnetic field. You didn't change the current. You just imagined that, in fact, you imagine that this looks like this. And so you know that the force here would be ILB, which means the force on the top would still have to be ILB, even though this is not here. Like, the fact that this is here doesn't change what the force is on this top. We just know what the force is here because we have to satisfy this condition. Total force acting on the loop is 0. It works here too, even though there's not an actual current.